here. So yes, we are kind of in the middle of section 2.1. Okay. We really don't have too much left on it though, just a little. Okay, so just from Wednesday to Monday, kind of seems like you forget stuff over those several days. And that was always weird about Monday, Wednesday classes to me, but I guess it's really not any different than Tuesday, Thursday, but feels weird. It feels different. Okay, so we have talked about how to write down sets. Okay. So we use in roster notation, we use a capital letter usually, and then an equal sign, and then curly brackets on both ends. And then for roster method, we list out the elements in our set. Okay. And then we had a little bit of vocabulary there. We said two sets are equal. What do we have to have for two sets to be equal? Do you remember that one? They have to have the same stuff in them, right? The term there, you can say elements or members, so they have to have exactly the same members, exactly the same elements in order to be equal. Then we also got a little bit of notation here, this thing that looks like absolute value. Anybody remember what it is? It's what it's called or what it means. I'll take either one. It's a cardinal number. Good, that's the harder one. Yeah, it's called the cardinal number. And it is how many members, how many things we have in each set. Okay. And it looks like absolute value. So then we had one more definition. We said, so backing up, two sets are equal if they have exactly the same elements. But we had this other notation here, this squiggle. Okay. It's equivalent, good, it's equivalent. So we can say one set is equivalent to another set if they have the same cardinal number, if they have the same number of things in it, same number of members. Okay. That's the short version of what we've talked about so far. Okay. And then the next thing we want to talk about is a different way to write down sets. Okay, so we've looked at roster notation like these, where we just list out the sets, list out the members of the set. Okay. But if we start having sets where we have a lot of things inside of a set, like we want the numbers 1 through 100 or something like that in our set, then that gets kind of annoying having to list all of it out, having to write all that stuff out. And then sometimes, I know this is called finite math, but sometimes we can even have an infinite number of things in a set. So if we said we want our set to be the set of all even numbers, then if we tried to list all those out, we'd be listing forever, because you always have a bigger number, and they just keep getting bigger and bigger and bigger. Okay, so in cases like those, we have to use a different method to write the set down. And the other way we're going to write these down is called set builder notation. So the idea with set builder notation is that instead of listing out every member of a set, what we're going to do is we're going to come up with some way to describe all the members of a set. So maybe they all have something in common. So we'll say this is the set of things that all have this property in common. So with even numbers, that would be really easy. We would say this is the set of all even numbers. And we're done. We don't have to write them all down. Okay. And so with set builder notation, we're still going to have a capital letter. And then we'll still have equals in the curly bracket. Okay. But then when we write these down, we use some variable is how we start out with. X is what the textbook uses most of the time. You could use anything, but we'll say A is the set of all X's. And then we'll have a vertical bar. And it's kind of like just one side of the absolute value. And the way you read that vertical bar on these sets with set builder notation, you read that thing as such that. Well, if I can write such that. That's the vertical bar part. Okay, so we're going to say this is the set of all x's such that, and then we talk about the property they have. Okay, so maybe we'll say, since we've talked about the even numbers, we would say x is an even number. Okay. And that would be fine. Okay, that would be our set. It's the set of all these things, and the thing that they have in common is that they're all even numbers. Okay. Okay, so that would be set builder notation. Okay. Let's see if we can write down another one here. This one says use set builder notation to represent the set y, and we want y to be the set of all even integers. Okay. So really quickly, we have integers. What types of numbers are integers? Whole numbers, and there's a little bit more that we can do with them. Let's start from the bottom and build our way up. Okay. The numbers we count with, like 1, 2, 3, 4, 5, those are the natural numbers. That's what we call those. If you include 0, then we get the set we call whole numbers. And then the next thing we want to do, we have to have positive numbers and negative values. Okay? So if we have positive and negatives, then we call those the integers. Okay? So integers are positive and negative whole numbers. Okay? So let's write down our set. Okay? We can just do it in words, so nothing wrong with that. We can say y is the set of x's such that, and then we've got really two things we have to incorporate here. We need our numbers to be even, and we need them to be integers. All right, so we could say x is an even number. And x is an integer. Okay, so that's one way we could write that down. So if that works in words, okay, nothing wrong with that. If we're dealing with more math-related stuff, usually we have shorthand for a lot of that. So one thing we have shorthand for, you don't have to use it, I just want you to see it so you know what it is. So one thing we have shorthand for is this set we call the integers, the positive and negative whole numbers. The symbol for that group of numbers looks like a weird Z. It's like a Z with 2 bars down the middle. And if I remember correctly, the reason why we use Z goes back to the German word for integer. So if that doesn't make sense, that's okay. It doesn't make sense to me either. So Z represents the integers. So another way you might see this, instead of in words, x is an integer. Another way we could say the same thing is we could say this. We could say x, and then we've got this symbol that looks kind of like a curved E. It's in Z. So all this little symbol means is this thing on the left is a member of this thing. So this would say x is an integer. Oh, that's it. Just want you to have seen that so you know where it's coming from if you're into it. Other ones you might see, the natural numbers, they have a symbol. And it makes more sense. It's an N, but it's with that weird script. And I have a really hard time handwriting that one, but it's like an N with two bars. It's really ugly, I'm sorry. That's natural numbers. Integers are Z. And then one you've probably seen, so real numbers, and it's double barred R. Okay. And those are the most common, and then just for the sake of being complete here, rational numbers. What are those? Those are ones we can write as a fraction. Rational numbers. So those are a Q, and it's even weirder. It's like it's Q for quotient. It's a fraction. You don't have to deal with that much, but just so you'll know what they are, if you, or at least have an idea of where it's coming from if you see that. Okay. They're there. Okay. All right, so those are set builder notation, and again, there's more than one way you can write it. Okay. You can do it in words. Sometimes we have symbols we can use. So as long as we get it described, then we're in good shape. Okay. All right, so one more here, one more. Get a little bit of practice. Next thing about this one tells us we want to represent the set, we're calling it J, of all natural numbers less than 10. And it wants us to write these out using both methods. We want to do the roster method and set builder. So let's start with the roster method. There we would have our set J. And then we just list out the elements. So this says the natural numbers less than 10, so that's our counting numbers, less than 10. So what's going to go in there? Start with 1. And then 2, 3, 4, 5, 6, 7, 8, 9. What about 10? No, because it says less than 10. Okay, if it said less than or equal to 10, we would do 10, but it says less than 10, so there we go. It's 1 through 9. That's roster method. Then with set builder, and we would say we've got set J. That's the set of x's or some variable. And we got our bar that says such that. And then what do we need? We can do it in words, just if we want to in words. So we could say x is a natural number. Yeah, you could say, you could say less than 10. I'm gonna even break it down, but I'm gonna say x is less than 10. But you could do it in one sentence like that. X is a natural number less than 10. That would be okay. Like I said, there's more than one way you can write them down in set builder. This first part, if you wanted to use the weird symbols, you could say x is in natural numbers and x is less than 10. That would be work also. Questions on that one? So on ones like this, it's probably, if you have a choice, roster method's probably easier, right? You just list them out. But if it said we want the set of all natural numbers less than 1,000, then set builder is going to be easier because you don't want to have to list out 1,000 numbers. just kind of situational. Okay. All right, so that's set builder notation. Next up, we have two special sets we need to talk about. So these kind of have a special place. Okay, the first one is the set that has nothing in it. Okay. What we call the empty set, or the null set. You'll hear it called the null set sometimes. And it's just the set that has nothing in it, has no elements, no members. And our symbol we use for the empty set, if you look down at the end, it's just like an O with a slash through it. When I write that by hand, it looks like that. Okay. That's the empty set, has nothing in it. One little, it's a little ticky-tacky, tedious thing, but just so you're aware of it. Okay, Hawks will count this wrong if you mess it up. If we're trying to say a set is empty, we need to write it like it says it up there, A equals, and then that symbol. The empty set is the only set that we don't put curly brackets around. Okay. So this is incorrect, okay? And Hawks will count that wrong, even though it's real ticky. This is the empty set. Okay. The reason why this one's wrong, it gets a little mind bending. Okay, you're thinking kind of a little beyond where we're at here, but this is a set that has one element, and the member of that set is the empty set. Okay, so that's a little, starts getting confusing when the members of one set are other sets. Okay? We're not really gonna get there, but that's why that one's technically incorrect. Okay, we don't want that. We want this. Okay, there's the empty set. Let's see if we can, let's look at these situations and see if we can pick out if that would be empty or not. Yeah, set A says that's the set of negative numbers less than 100. Would that set be empty? About -2, would that be in there? -3, -4. This one's not empty. Okay, all negative numbers are less than 100. Okay, so that's really have infinitely many members in that set. So that one's not empty. But what about B? It says the set of any state that contains the letter Q. Can you think of a state that has a letter Q in its name? Me either. And so we won't spend too long thinking about it, but here set B is the empty set. There's not any. That is the empty set. And next little thing here, it's always tough for me. It says give an example of an empty set. It's one of those things that's like really easy. There's infinite amount of them you could choose from, but when you try to think about one, you overthink it and it gets hard. Can you think of a set that would be empty, that would have no members? The oceans that don't have water in it. Okay, that's a good one. Yeah, that's good. Okay. Think of any other ones? Always way overthinking. You can think of like the set of Walmarts that have more than 2 cashiers working. Okay. That'd be an empty set. Things like that. So, okay. All right. So our next special set is what we call the universal set. or sometimes we'll just call it the universe. And the idea is that the universal set has everything in it. But it's a little bit contextual, okay, or it is a lot contextual. What we mean by that it has everything in it, really depends on the context where we're working. Okay? If we're working with a bunch of sets that have numbers in them, then we would say the universal set has all the numbers, okay, all the possible numbers. If we're working with sets that have letters out of the alphabet, then we would say the universal set's the set that has all the letters of the alphabet in it. Okay? So it just kind of depends on the situation you're working with, how big you think about the universal set being. But our symbol for it's really easy. It's just a capital U for the universal set. And it gets its name because if you are working with sets of anything, then the universal set is the universe. Universal set there. Okay. All right, so now that we've got those two ideas, the set with everything, the set with nothing, we're ready to talk about the set operation, okay, something we can do with sets. And the first one of those we're going to look at is called the complement of a set. Okay. And the complement of a set, okay, is the set of all elements in the universe that are not in the original set. So we want the complement of set A. That's going to be all the elements in our universe that are not in set A. Okay. You can think about it kind of like the opposite. It's like the opposite of that set. It's everything else, everything that's not in it. And our textbook chose to go with this tick mark or like a single quote as the complement symbol. I don't know if that's the best choice. It's not very universal. Not everybody uses the same symbol for complement. So just so you're aware, sometimes you'll see a superscript C. That can mean complement. Sometimes you'll see just a bar over the top. That can mean complement. But in this class, every time we say complement, we use the tick mark. Okay. Just all the elements that are not in that set, all the elements in the universe that are not in that set. Okay. So let's see. Get this out of the way. Let's say our universe is the letters A, B, C. Okay. That's all we're working with. Then if set A just has the element A, then what's A complement going to be? It's going to have everything that's not in here. So in here would be B and C, B and C. Oops, sorry. Went the wrong one there, B and C. And one other little thing to point out before we leave this, if you had the set A complement and you wanted the complement of that, what we're going to end up with. So we've made it to here, and we want the complement of this. So we want the set that has everything that's not in here. What's that going to be? That's going to be back to here, right? We're just going to have A. So that's just going to be our original set A. So if you do the complement twice, it cancels itself out. And so A complement complement. Okay, it's just the same thing as A. Okay. All right. So let's look at a couple of examples. We'll be done with this section. Okay. Our textbook is getting a little bit old. Okay. It's time for a new edition to come out. And this is one of the examples that kind of points that out, because on this example, they're going to try and explain Twitter to you like you've never heard of it before. And so, like, it's this new and upcoming thing. So just know it's because our textbook's getting kind of old. Okay. Do any of you even still use Twitter? Any, like one or two, not many. Okay. So it's kind of faded out with the younger generations. Here we go, though. Okay, it says Twitter is a type of online social media where users can post tweets that are up to 140 characters long, and they're longer than that now. In the world of Twitter, you can keep up with what other users post by following them, and in turn, other users can follow you in your tweets. And it's like you've never heard of that concept before. Okay. So here are our sets. Okay. Our universal set's going to be the set of all registered users on Twitter. Set A is going to be all the users on Twitter that follow you on Twitter. Okay, so your followers. And then we got one more, set B, which is all the users on Twitter that we do not follow. So all the people that we don't follow. We want to figure out the complement of A and B. So we want A complement. So A, that was a set of all Twitter users that follow us on Twitter. So if we want the complement of that, who's going to be in there? People that what? A is the people that follow us. So A complement would be the people that do not follow us. Okay, it'd be all the people that don't follow us. Okay, so we can write that down in set builder notation. If I can do a bracket. And I'm not going to say as a registered Twitter user again, we get it. Okay. Say X does not follow us. Okay, and B complement. So B is a set of Twitter users that we do not follow. So B complement would be people that what? That we do follow. Okay, it'd be all the people we do follow. So X is a Twitter user we follow, I guess, something like that. Maybe. Okay, so complement's kind of like the opposite. You're just having to make sure you're working in that universe, whatever universal set you're dealing with. Okay. Let's look at one more. Okay, we got it. Okay. On this one, it says our universal set is the set of books published in the United States in 2014. And set A, set of things that are in use, so books published in 2014, and we read that book as an ebook. Okay, so set A is a set of all books published in the US in 2014 that we read as an ebook. Okay, so first thing we want to find a complement. So what books are in there? It's going to be we can copy them a little bit. All right, we can say it's books published in the U.S. in 2014 that what? To be an A, we had to read it as an ebook. So to be an A complement, what? We did not read it as an ebook. Right? Did not read it as an ebook. Okay. Explain the first part again. Oh, okay, yeah. So I'm just copying them. There, all this is this says that X is a member of this set, so it's just in the universe. And to be in our universe, it just says it's a book published in the U.S. in 2014. So I'm just cheating. Instead of writing it's a book published in 2014 in the U.S., I'm just saying that again. That's what they did on theirs too. Just saying this is one of these books, and we read it as an ebook. Okay. So now we got another question. Is it possible for us to have read a book that's in this set? We do. It is. How could we do that? How could it have happened? This is just the ones that we read as an ebook. So there could be a book in here that or a book. Is it possible to read a book in A complement? Yeah, it's possible there's a book in here that we read, but we did not read it as an ebook. Okay. Questions there? No? Okay. All right, so we're done with that section. We can get 10-2 to open up here, maybe. All right. So in 2.2, we're still working with sets. Okay, so we're still using that information we've talked about in the last section. Okay, but two big things. We're going to talk about what it means to be a subset of a set. Okay, and then we're also going to start looking at using these things called Venn diagrams. You've probably seen those before. Maybe you didn't know to call it a Venn diagram, but you've probably at least seen them before. They're really helpful when you're trying to keep track of the relationship between different sets. We're going to use those as we go through here. Really, we just have a definition and then talk about these Venn diagrams. So you've probably seen a Venn diagram. All it is you've got ovals or circles representing two groups, and then they may overlap or they may not overlap, doing that kind of thing. You even see them in memes sometimes. Okay? Like if you think about it, you can think about something. Okay, so nothing too complicated about them. The reason why they get the name Venn, okay, it's the person's name. He's a British logician, did logic, named John Venn. And they can help you out thinking your way through lots of different things, but they're real big in set theory, for sure. Okay. So, all it is, okay, we start off, and lots of times the ones you see outside of class don't do this, but what we're going to do is we're going to start off with a rectangle, okay, to represent our universe, our universal set. And then inside of that, anytime we want to represent a set, we use a circle or an oval. It doesn't have to be a perfect circle to represent our set. Okay. So let's look at one. Okay. And so here's a Venn diagram. Got 3 sets represented in it, and it tells us our universal set here are all the X's such that X is in the English alphabet. So our universal set's all the letters in the English alphabet. Okay, and then we've got 3 sets represented on here: set S, set T, and set V. And then they've got their members, their elements listed out beside them on here. Okay. So we've got a few questions to answer just to get us ready to look at these things. So it says, list the elements of set S, T, and V in roster form. Okay. So all that means is we just list them out. So if we want to list out set S, we can get them right off the diagram, right? It's just, we've got K, A, and S in there. We'll set T. It's probably a little harder to see what these are up here in the back. That color doesn't show up great, and it's a little bit small. That's a lowercase t, a lowercase j, and then M and D are a little bit easier to see. Okay. And then set V, the letters E, C, and P. Okay. That's it on that. Nothing new really. I'm just picking it off of the Venn diagram. So, okay. B, let me flip over so you can see the question. B says find that things that look like absolute values. So what does that mean again? Cardinal number, and that's what is cardinal number. It's how many things we got in the set, right? How many members we have in each set. So if you remember that, we can just count them. So cardinal number of set S. Got 3 letters in there, so that's 3. Cardinal number of set T. We've got 4 letters in that one, so 4. And cardinal number of set V. 3 in that one again, so. Next one's a little tricky. Okay, it says find T complement. Find T complement. Okay. So I kind of played a trick on my other class and let them get it wrong. I won't do that to you. They didn't seem to like it. Okay, so we'll just talk about it. It's very tempting to say T complement is KASECP. Not the members that are not in T. Okay. But that's not it, okay? Because we want everything that's in the universe, everything that's in the universal set that's not in T. So these are not the only letters that are in the rectangle, right? They're not the only ones that are in the universal set. The universal set's all the letters in the English alphabet. So we actually have a big annoying set to write down for T complement. We got to write down all the English letters except these 4. Okay. And so on the test day, I will do my best not to give you one this long, just because it's tedious. Okay. But we want A, B, C, not D, okay, because D is in our set T. Okay. Then E, F, G, H, I, not J. J's in T. K, L, not M. M is in T. N, O, P, Q, R, S, not T, because T is in T. U, V, W, X, Y, Z. Okay. Sorry, that's a big set to have to list out. But it's all of the elements that are in the universal set, that are not in T. Okay? It's not just the ones that are in the other sets on the Venn diagram. Okay? They could have listed all these like out here, like outside these circles, but they didn't. But you got another there because it's listed as part of the universal set. Okay. All right, one more. We don't have to write anything down for this one. Okay. Last one says, is set S equal to set V? So does this set equal this set? What do you say? No, they're not equal, because what do they have to be equal? They have to be exactly the same. I gotta have the exact same elements in there. And these letters are not the same as these letters, so they're not equal. But then the next question says, is set S squiggle V, or is it equivalent to V? Yeah, it is, because in order to be equivalent, they just have to have the same number of elements, the same cardinal number. So they are equivalent. They're not equal. Okay. All right. That's that one. Okay. Look at one more here, just reading the Venn diagram. And again, our textbook's getting a little bit old, so the information is a little bit out of date. Okay. It says there's an increasing number of electric vehicles on the roads in the United States. That's still true. It says the number of charging stations available for these cars varies from state to state. States with the most electric charging stations are California, Florida, Oregon, Texas, and Washington. Okay. It may or may not be true now, I'm not sure. Then we're going to list them out as sets. Okay. So set U, the set of all electric charging stations in the United States. That's our universal set. And then for each of the other ones, like for C, we're taking the set of all charging stations in California. Okay, so it starts with a C. Florida is all the charging stations in Florida, so we get set F. Okay. So there's first letter of the state. Okay, that's how we're labeling them. Okay. Then we get a Venn diagram. And on this one, it's a little bit different because there's so many things in each set. Instead of listing them all out, like you could list out like the address of all the charging stations. But there's so many of them, instead of doing that, they've just given us the cardinal number, so we know how many are in each one. Okay. And then we just have a few questions to answer. First one says, which state has the most electric charging stations? So these are the top 5, right? These have the 5 most, so whichever one out of these has the most is going to be the winner. So which one has the most? California or C, you can say either one. Okay. 5,415. Okay. All right, next, so what state has the second highest number of charging stations? T, Texas. Okay. You have to be a little careful on that one. You might not have noticed, but on a Venn diagram, the size of the circles doesn't necessarily have to do with how many elements it has. It's not necessarily to scale. Here, Texas has the second most charging stations, even though the Florida circle's bigger. Okay? Just the size of the circles don't matter on a Venn diagram. Okay? So Texas does have second most. Okay? Number 3 says, how many electric charging stations do the top 5 states have altogether? How could we figure that out? Add them all up, yeah. So we would just, these are our top 5 states, so this plus this plus this plus this plus this. Okay. It's like 10,000 and something, I think. Let me know the number when you get it now. Okay. Sounds right, so that's the top 5. Okay, so if you add those up, get that number. And the last question says, how many charging stations are in the United States but not in one of the top 5 states? How could we figure that out? It's a little trickier. Have any ideas? Well, this is the total. Yeah, this is the total in all the United States, our universal set. So we can take that number and subtract, and we get our number for outside of the top 5 states. Okay. Okay. Questions on that one? It's not too hard. Okay. All right. Mondays. Okay. So next thing is a subset. Okay. So what do we mean when we say a subset? So here, if we have 2 sets, we've got A and B. It says B is a subset of A if every element of B is also an element of A. So another way you could say that is the set B is like inside set A. Okay? Everything in B is also in A. That's a subset. And our notation for that is a little weird, but it's like a C, but then it has a line under it. Okay? So that thing you can kind of think about it as kind of similar to saying less than or equal to. And it has the similar idea there, but just instead of that V shape you get with less than or equal to, we got like a C shape. We can't say one set's less than another set, but we can say one's a subset of another. Okay. That's a subset. So next we need to think about how we could represent that on a Venn diagram. Okay. Represent one set being a subset. So let's look at an example here. All right, so this one says our universal set is a set of all students at State University. W is a set of students at State University that are majoring in computer science with a minor in business. And then set Y is a set of students at State University majoring in computer science. So if we're going to draw this Venn diagram, we have to think about our relationship between W and Y. Which one's going to be a smaller group, W or Y? W, because on W it says this is all the people majoring in computer science, but all these people also have a minor in business. On Y, it's just the people majoring in computer science, and we don't care what their minor is. They could have a minor in something else. So the idea here is that everybody that's in W, they're all computer science majors. They're all also going to be in Y because these are just computer science majors. Does that make sense? Okay. So when we draw our Venn diagram, it will start off with our rectangle for our universal set. And then usually it helps to draw the bigger set. So our bigger set here was Y, the set of all the computer science majors. There's Y. And then where's W going to be? Everybody in W is also in Y. So W is like somewhere inside Y. And your picture doesn't exactly have to be like this, as long as you get the relationship right. So Y is all the computer science majors, and then W is all the computer science majors that also have a minor in business or whatever it was. Okay. So W is a subset of Y here. Okay. So if we took all the people in this room and made that a set, okay, then we could make a subset. We could say a subset's all the people in the room that are left-handed. Got any left-handed people in here? Yeah. So you would be in our subset, right? Because you're still in the room, right? But you're in your own special little set. Okay, your left-hand club. Okay. That's a subset. Okay. Questions there? We don't have much left, I promise. Let's do another one. Let's draw another diagram. Let's try to draw this one. So it says our universal set is a set of computers. It says A is a set of iPads, and B is a set of all tablet computers. So can you be an iPad and a tablet computer? Yeah. So then the next question are all iPads tablet computers? Kind of depends on how you think about it, but yeah, we can say so, right? Because all iPads are a little flat computer you can hold in your hand. Yeah. So they would all be tablet computers. And if you're not sure, think about it the other way around. Can you have a tablet computer that is not an iPad? Yeah, you can have like a Samsung thing or an Android or Windows or something like that. You can get a tablet that's not an iPad. So which one's the bigger set? A or B? B is the bigger one. So that's all the tablet computers. And then in there we've got iPads, the type of tablet computer. Okay. Good. Nah, like the explanation and all that. Yeah, no. Nah, because we got it up there, so we're good there. We got them labeled, so. Okay. All right, so one other idea with subsets. Okay. There is a weird situation you can have with subsets if you just take the strict definition. The strict definition says that every element in set A is also in set B, their subset. So the weird thing that can happen is if you have two sets and they're both the same. Okay, so like set A is all the people in this classroom, set B is all the people in this classroom, then by the definition you can say set A is a subset of set B because we're all in both sets. Okay? So that's kind of weird, right? You don't really want to call it a subset if they're exactly the same sometimes. So to get rid of that one situation, that weird happening that can occur, sometimes we distinguish between just a regular subset and what we call a proper subset. So the only difference here is that in order to be a proper subset, there has to be some element in the bigger set that's not in the smaller set. So if we took our two sets again, if we said one set's all the people in this room, and then we made our second set all the students in this room, then I wouldn't be in that second one. So that would be a proper subset of the people in this room because they would have one element that's not in there. Okay. And we do have just a little bit different notation. If you look there at the end, the only difference is we don't have that bar on the bottom. So it's kind of like we've taken away the or equal to bar. So they can't be the same. Okay. That's a proper subset. Okay. Sometimes we don't care. Sometimes it's okay for them to be the same, and then we just talk about subsets. But we're talking about proper subsets, and we're getting rid of that case. Okay. All right, so let's look at an example here. Almost done. So here's a set X, has the numbers 1, 2, and 3 in it. It says list all the proper subsets. So since it says proper, we know we're not going to have the set 1, 2, 3. We got to leave that one out because it says proper. if it didn't say proper, we could use that one. Okay, so somebody give me a subset, you would say, of 1, 2, 3. So we just need, you know, some other combination of 1, 2, and 3 that's not 1, 2, 3. 1, yeah, 1 would be good. And then we could have one that just had 2 in it. We'd have one that just had 3 in it. Those would all be proper subsets. What else? You see any other ones? We can't have 1, 2, 3, but we can do other combinations. Yeah, we could do 1 and 3. Yeah, we could do, what else? We could do 1 and 3, we could do 1 and 2. Or we could do, we got 2 and 3. Here, just remember order doesn't matter. So saying 2 and 3 is the same thing as saying 3 and 2, right? You can switch the order, that doesn't make a difference. So, okay. So we've got all the ones that only have 1 member, all the ones that only have 2 members. But we're actually missing 1 subset. And it's kind of weird first time. Oh, good, yeah, good. So we can't do 1, 2, 3, right? So we can't go up to 3, but we do have one more on this end we could do. We did the 2s, we did the 1s. So what was the other one you said? The 0 one, the one that has no elements. So that set we call the empty set. Oops, sorry. Call the empty set. That's a little weird, especially thinking about it the first time. If that feels a little weird to you that the empty set's a subset, that's okay. It kind of does to me too, but it works out that way. Remember, we don't put brackets around the empty subset, the empty set. And you can always take a subset that's empty. So the empty set is a subset of any set. So it's going to be on the list. Okay. One more example. One more. Okay. We're getting there. We're getting there. There they are. Okay. Do this one. Okay. So this one stepped up. This one's a little bit longer because this one has 4 elements. So when we're listing them out, the list gets kind of long. So hang in there, or you'll be tired of doing curly brackets by the time you write them all down. It's the second time I've done this today, so I'm real tired of curly brackets. To me, it's good to start with the empty set so you don't forget. And then we can do all the subsets that would only have 1 element. So we do A, B, C, and then D. Okay. Yeah, and then we can go the ones that have 2, so that's good. We can do A, B. Yeah, bless you. C and D. What else? A and D, yeah. And then we got one more. I don't have one with B and C, I think is right. Is that all those? A, B, C, D, A, D, B, C. That's all those. And then we got one more group we got to do. Yeah, we got to have A, B, C. So you can kind of be systematic there. We left D out that time, so like maybe we'll leave out C next time. So A, B, D. And then leave out B. So A, C, D. And then leave out A. So B, C, D. All right, let me check it real quick. Oh yeah, we're missing something. So which one did you see? D. Yeah, we missed D and B. Okay. And then how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Missing one more. What we missing? Missing A and C. Yeah, missing A and C. Accidentally skipped a couple there. A and C. Okay. That's good question. Okay. Yeah. So how do I know how many we're supposed to have? Okay. A lot of times that's the only part we want to know. We want to know how many subsets. Okay. And if you get much bigger than this, it gets real annoying trying to list them all out just so you can count them. Okay. So we need a method where we can just figure out how many they're going to be, because lots of times we don't care what they actually are, we just care how many. So here's our little formula. Okay. So if we know the cardinal number of our set, so we know how many elements our set has, call that n. Okay. Then there are 2 to the power n subsets. And remember, if we're counting proper subsets, we got to get rid of that one case where the set matches the original set. So we subtract 1 if we're counting just proper subsets. Okay. So when we had 3 elements, like on the first one, to figure out how many proper subsets we would do 2 to the third power minus 1. So 2 times 2 times 2 is 8. And then minus the 1 for the proper subsets, we got 7. And on this last one, we had 4 elements. So I knew we should have 15 because 2 times 2 times 2 times 2 is 16 minus 1. So we had 15 in that last one. Okay. One more little thing to look at and you're done, I promise. Last slide. Okay. We're early too, so. I was feeling guilty till I looked at the clock, but I'll get you out of here, okay? One more little slide here. Everybody got what you need off that one? Okay. So we won't have to do a calculation, it's in here, but let's just think about it, okay? It says Dr. Williams is eating at a China buffet one afternoon and notices a sign that says, so many possibilities, you could spend a lifetime eating at China buffet and never have the same meal twice. Okay, so that's a pretty bold claim. So then he starts thinking about how many different plates he can make. Says they've got 16 items on the buffet. And says they could have all, none, I don't know why I would do none, waste his money, or some of the items. Okay, so we want to figure out how many different meals he could make. All that is subsets. We're thinking how many different ways can you pick subsets from our set of 16 things on the buffet. Okay. And since it says he can have all of the things on the buffet, that would be all 16 things on the buffet. So that's the set of itself again. So that means it's okay just to do subsets. We don't have to do proper subsets. So 16 things on the buffet, then if we do 2 to the 16th power, that tells us how many subsets we have. Okay. And I bet it's bigger than you're thinking. 65,536 different combinations. Now granted, one of those is an empty plate. Okay. Got that many combinations. Okay. And if you go all the way back to the claim, says you could eat there for a lifetime and never have the same thing twice, then what about that? Is that true? If you're eating there once a day, 365 days a year, how long would it take you to have to repeat? That would be almost 180 years. Okay. So unless you're planning to live to 181, then that's true. So, okay. Something a little bit more fun, probably not real fun, but it's a little bit more fun than. I'm sorry. Yes, it's always 2. Yeah, it's 2 to whatever power. And then the only difference, if you just care about subsets, you just do 2 to the power. And if you only care about proper subsets, you just subtract 1 at the end to take care of that case where they're the same. Yep, that's it. Questions? Oh, all right, get out of here. I'll see you Wednesday. If you didn't get on the sign-in sheet, I'll put it up here on the front table. Get on there on your way out.